Okay, so we're rolling. There we go. Okay, so in Calc 1, you investigated two primary problems in the subject of calculus. So calculus really boils down to these two kind of problems or situations. First one is you know how much of a quantity you have at every moment, and you want to know how fast the quantity is changing at every moment. The second primary problem here is you know how fast the quantity is changing at every moment, and you want to know how much of it you have at every moment. Okay? Some of you realized that that's what you were doing in Calculus 1. Maybe some of you didn't, but this is what you did or should have been doing in Calculus 1. It's talking about one of these two problems at any given time. Okay? So Calc 2 continues to explore both of these problems, but most of the course concerns endeavor number 2. Most of the course is going to be focused on endeavor number 2, and that's this one. You know how fast a quantity is changing at every moment. You want to know how much of it you have at every moment. Okay, so this first week, we're going to review the mathematics of that. We're going to kind of build this from the ground up in a week. So in my calc class last semester, we took about a month to build this. But we're going to kind of review that process in about a week. So I'm going to break this down into several principles. Okay, several principles. And so this is kind of like a important principle that comes before the principles, principle 0. And that is that variables vary. Variables vary. Okay? So what do you think when you see this equation, 2x minus 7 equals 0? What do you think when you see that? Solve for x. And what do you get when you solve for x? 3.5, right? So when you see that, you think x equals 3.5. Could x be 4 or 10 or negative 0.5? No? Yes? No. Okay, he said it could be, say it could be 4, and they said then the equation wouldn't be true. So could x be 4 or 10 or negative 0.5? Does it feel uncomfortable? Suppose the exact same x that came from 2x minus 7 was defined this way. The number of hours elapsed since your plane left the ground. Could x be 4? Could x be 10? Long flight, right? Could x be negative 0.5? You're saying yes. Why? Yeah, so that would be like a half an hour before the plane took off. So negative still makes sense, right? So, maybe 2x minus 7 is something like the time, so it ends up being the time elapsed after takeoff when you got your peanuts or something like this, or your drink, or you went to the bathroom for the first time, okay? But x could take on every real number, okay? And there was a point in time when this plane flew that it was taking on every real number. A quarter of an hour, an hour and 10 minutes, right? So as time went by, x took on all these values. Just because 2x minus 7 is isolating some situation, it doesn't mean that x is 3.5 and that's the end of the story, right? So in this situation, x at some point in time took on all those values, maybe starting from 0 or even starting from some negative value. Okay, so x takes on many values, any real number. And that's the way we want to think of variables. In a given situation, they stand for a quantity, and that quantity is going to change, and so that value of that variable changes as the quantity changes. All right? So what about this? dx, variable dx, what would that represent in this situation? If x is the number of hours elapsed since your plane left the ground, then what might dx represent? And so if it's a change in x, then it's a change in what? Right, so yeah, so dx is a change in the number of hours elapsed. A change in the number of hours elapsed. So how is x equals 3.5 different from, say, dx equals 3.5. So x equals 3.5 means, so x was changing as you were flying, right? And as you were flying, there came this moment, x equals 3.5 hours. And then it was gone, and then x was greater than 3.5, right? But what would dx equals 3.5 mean? What would that mean? So dx equals 3.5. Okay, so a difference between, so he said a difference between, say, x1 and x2. So, right, so from one value of x to another value of x, there was a 3.5 hour interval of time, or a change in time, say, and that could be starting from 1 hour. So it could be from 1 hour to 4.5 hours for x. You'd have a change of 3.5 hours. It could be from, 5 hours into the flight to 8.5 hours into the flight. That would be another example of your change in time being 3.5 hours. Okay. First slide. Any questions on this? Okay, so we're gonna. That's principle 0. Okay, and so we want to also think of dx as a variable, right? So I said dx equals 3.5. Well, if our x initial, say xi, was 2 hours, so starting from 2 hours, we can have a change in time of 3.5 hours, but then that dx could change, right? So dx could be increasing from 3.5. So it would be starting from 2 hours, 3.5 hours gone by, 3.6 hours gone by, 3.7 hours gone by. So dx itself we want to think of as a variable. It would be increasing as x increases, the amount of change. Okay, so that's principle 0. Variables vary. Okay, so now principle 1. Rate of, so we're talking about, you know how fast the quantity is changing at every moment, and you want to know how much of it you have at every moment. What does rate of change have to do with that? What does rate of change have to do with that problem that we're reviewing the mathematics of? Okay, so in the first part of that statement, you know how fast the quantity is changing. Well, that's rate of change, right? That's rate of change. So certainly, the principle of rate of change is very important here. Okay, so we're going to review the basis of rate of change. So here's an example. You're buying trail mix that costs $3.20 a pound. You've got some in your bag, but then you decide you want more. Okay, what additional costs will you pay for 1.5 more pounds of trail mix? I want everyone to figure that out. No, by yourself. Everyone figure that out. And write out your work. Don't do it in your head. Write out your work. How much more would you pay for 1.5 more pounds of trail mix? So someone had said the answer. What is it? 80 cents? $4.80. Did you get $4.80? Okay, just to make sure that's what you should have gotten. All right, so a really important thing in mathematics is that we can use mathematics to model real-world situations. And so we've got a whole language of symbols, right? A language of symbols that we use to model real-world situations. So we're going to practice that here, because anytime you come to an application or a situation in a problem, you want to model it with the symbols first before just diving into calculations. So let's practice that. So I've got a set of symbols here, x, y, dx, dy, and m. And I haven't really given you any clue as to what those would be, but I think conventionally from your past calculus and math experience, I think there's some implication. So what I'm looking for here is a phrase. Define each variable below completely and precisely. So we're looking for a phrase. X is what? It's the temperature in my room after midnight. That's an example of what X could be, something like that. Or it's the length of my hair starting from February 1st. Okay? Something like that. Okay? So, and let's just do X together. So what would you, we'll do X together. What would you guess that X is? What do you think X is? As a phrase describing a quantity in this situation. What's that? He wants the weight of the trail mix. Okay, so is it the total weight or the total number of pounds or the additional number of pounds? Okay, it's going to be the total. It's going to be the total. X is going to be the total number of pounds, and I think you'll see why very carefully soon when you finish this out. Okay, so finish these and go ahead and get a partner and kind of work on these together, or group of 3 at the largest. So let's hear from some of you what you came up with. So volunteer, what'd you come up, you and a partner, what'd you come up for Y? Y is, yes sir? Total cost. Total cost. In dollars, right? So the total cost of X number of pounds in dollars. All right, so then what would dx be? Somebody knew. What would dx represent? Yes, sir? Change the number of pounds, right? Some change in the number of pounds. Okay? And then dy? Change in the cost, right? Change in the cost. All right, what about m? What's kind of implied by m here? Somebody, how about in the back? Somebody knew? What did you say? M was. Okay? So yeah, the rate of change of so it's the rate of change of what? Cost with respect to number of pounds, and that was given at $3.20 a pound. Okay, so anytime you start a problem, anytime you start diving into some kind of problem, you don't want to dive into making formulas and cranking out calculations. So I'm supposed to do this first and then this. We want to understand the problem and do this. Model your quantities with symbols, right? Variables. Model the quantities with these symbols. It doesn't have to be X and Y. X and Y are commonly used, but model it somehow so that you have these variables and you know what everything means, right? And this is about understanding the situation, really understanding it first, rather than just diving in and thinking, what do I do? Oh, I do this, and I do this, and I'll get the answer. Okay? We want to understand the situation. Part of that is modeling with variables. Okay? So, given what we know, is X, so X is variable, but given the setup, is the current value of X known? Is the current value of X known? Okay? What about Y? No. What about dx? Is dx known? What is that? So for this particular situation, the current value of dx, right? Before we said dx can change, but given what we have here, we know it's 1.5 pounds, right? And similarly, m is our 3.2. Okay, so those are the two values that were given in this current situation, dx and m. All right, so I asked you to do a calculation earlier. So now what I want you to do is, I want you to write an expression using 2 or more of those 5 variables, x, y, dx, dy, and m, that represents computing the answer that you did earlier. So earlier you said, I asked you to calculate the additional cost for 1.5 more pounds. So I want you to form a formula that represents what you did, okay, to answer that question using two or more of the symbols there. Is the task clear? Yeah, you're creating a formula that would represent the calculation you did here. To answer that question, what's the additional cost you would pay for 1.5 more pounds? So what would that be? Which variable would that be? She's saying dy. Agree with that? Okay, so yeah, dy would be the start because I asked you to calculate a change in cost, the change in cost. And so how did you calculate that change in cost? Yes, sir. MDX. So you took your rate of change, $3.2 per pound, and you multiplied it by the change that we knew in pounds, which was 1.5, right? 1.5. So this formula right here is the way we want to understand that value of m. This formula is the way we want to understand the value of that constant rate of change of 3.2. We say that given any change in pounds. So if you put 2 more pounds in your bag, how would you calculate the change in cost? If you put 2 more pounds in your bag, how would you calculate the corresponding change in cost? Multiply by 3.2, multiply by m. If you put 10 more pounds in your bag, you're going to multiply by 3.2 to get the corresponding change in cost. So this is how we want to understand this. What does $3.2 per pound means? It means that for any change of pounds in your bag, to get the change in cost, you'd multiply by the 3.2. Okay. Does it make sense? So this little formula, you inherently knew what to do, but this models that. So this dy equals mdx is the math behind what you did to do that, to find out what your change in cost was. And that formula modeled that way with those symbols is really, really important, okay? Okay, so now, oops, got too much. So you take 0.4 pounds out of your bag and return it to the bin when no one's looking, okay? When no one's looking. So I want you to review the meanings of these variables and then decide if you know them or not. Know them in this situation, know what their current values are, okay? So review the meanings of these three and then decide now in this situation, do you know the values and what are they? Go. Okay, remind me of what dx meant again. Somebody knew? What was dx? Remember? Yeah. The change in number of pounds, and what is it now this time? She wants negative 0.4. Agree? Yep. It's still the change in number of pounds, and now it's negative 0.4. Okay? What does dy mean? What does dy mean? Change in cost? Do we know it? Could we find it? Yeah, right? So what did we say? Given any change in pounds, what's our change in pounds now? Negative 0.4. The change in cost would equal? 3.2 times that. And why is that true? Because 3.2 is a constant rate of change. It's a constant rate of change. Always stays at $3.2 per pound. So given our change of negative 0.4, we would just multiply it by 3.2, and it would this time give us negative 1.28. Meaning that what? What does that mean? Negative 1.28? our cost is that much less, right? The cashier is not giving us money, okay? We're still paying for it, but now our cost is this much less than what it was before. So M is the same. It's our constant rate, $3.2 per pound. Okay. Questions on constant rate of change? And here, this is the whole deal right here, constant rate of change. So for instance, 70 miles per hour, another example, 70 miles per hour. Does it mean that every hour you go 70 miles? Is that what it means? Every hour you go 70 miles? If it's, you're on cruise control, straight, flat highway, 70 miles per hour. Does it mean every hour you go 70 miles? Is that all that it means? It means a whole lot more than that, right? You know how far you go in a half a mile. How far do you go in a half a mile? You would take a half times 70 and you'd get 35 miles. You know how far you go in 2 hours. Change in time of 2 hours. Times 70, 140. So there's a lot broader meaning of this than you go 70 miles every hour. And that broader meaning is captured in this equation. For any change in time, your change in distance is 70 times that change in time, right? In 10 hours, a change of time in 10 hours, how far do you go? 700 miles, right? 70 times that change in time. Okay. Another example. A soldier lowers an American flag from the top of the pole at 0.75 meters per second. How much does the height change from 0.6 to 2.4 seconds since the flag left the top of the pole? All right, so I'm going to tell you what y is. Y is defined as the height of the flag in meters. Y is defined as the height of the flag in meters. You're going to define the rest now. So what would x be? What would y be? dx, dy, and m. See if you can do it in 1 minute. Can you finish that in 1 minute? And check it with the person next to you. Okay, somebody new. What did you think x is? How would you define x? Have it right here. In the gold shirt. Did you get it? X? Yes, sir. Okay, so we want to be more specific than that. So what? Okay, time in seconds. Yeah, so we need a starting point in that. So since when? Since when? Yeah, so number of seconds, there's different ways to phrase it, but just time or time in seconds really is not specific enough. We need that reference. Where does our time zero start, right? Where does our time zero start? So number of seconds since the flag left the top. I already told you what y was. So dx is a change in the time in seconds, or a change in the number of seconds. dy is going to be a change in the height. And then m is the constant rate of change. I got messed up there. What is the constant rate of change? 0.75? So y is defined as the height above the ground. So the constant rate of change is? Right, as time increases, the height decreases, which means that we have to have a negative rate, right? Negative rate. So the context tells us lowers at 0.75 meters per second. We define that height variable as height. So positive is upward. So if it's coming down, that constant rate is negative 0.75. Okay, so write an expression that's going to compute the change in height. What expression will that be to compute the change in height from 0.6 to 2.4 seconds? Generally, how would we calculate that without getting into the numbers yet? The change in height. So how much does the height change? dy equals mdx. We know that m is our negative 0.75, and what is dx now? What's that? 2.4 minus 0.6, right? So that dx is, this change in time is 1.8 seconds, starting from 0.6 to 2.4. So our dx would be 2.4 minus 1.6, or 0.6, sorry, 0.6 or 1.8. And then that would be times our negative 0.75. Anyone got an answer? The height changes by negative 1.35? Negative 1.35 meters. Okay, so now I want to change this up a little bit. And rather than saying how much does the height change from 0.6 seconds to 2.4 seconds, I want to say how much does the height change from 0.6 seconds to x seconds? How much does the height change from 0.6 seconds to x seconds since the flag left the top of the pole? So that the final time that we're looking at is now, we're thinking of it as a variable. Starting from 0.6 seconds, we're going to think of 0.65, 0.7, 0.72, 0.73. X is increasing. And as x increases, what happens to the change in height? It gets bigger negative, right? It gets bigger negative. So it's going to be a larger negative change as x increases. Again, variables vary, right? So we know this could be about dy equals mdx. dy is our change in height, but now that's a variable, right? So that itself is changing. That change in height is changing. M is our constant rate. dx is our change in the number of seconds. So really what we have here, this change in height then is a function of the change in the number of seconds, or the number of seconds x. Okay, so the type of function that this is called a net accumulation function. Okay, this is equivalent to asking what is the net accumulation function for the flag's height beginning at 0.6 seconds. So what do we mean by that? So net means what? The change since our starting point. So we're talking about how much change, right? That's what net accumulation. And accumulation means, in this case, the accumulation of height. Or the loss of height, right? So accumulation can be positive or negative. All right, so net means not the total height, but the change in height. So we're going to use this to mean our net accumulation of height, capital A sub h of x. This is a function of how much time has gone by, x. So, can you write the formula or the rule for this function? Can you write the rule for this function that would give you the net accumulated height starting at 0.6 seconds? Can you do it? So this is like our dy, right? This variable a sub h of x, function notation, is representing dy. So can we write the rule that would give us the net accumulated height at any value of x? Hint. Okay, we're going to have to figure out what that is, right? 30 seconds to a minute to think about it and compare with the person next to you. See what you come up with. Have an idea? When you have your what's known as the problem. Okay, so what is M? Negative 0.75. Does it change? No, it's a constant rate, right? So it's coming down at negative 7.5 meters per second. So then what's left is dx. So what is our change in the number of seconds if we are calculating what the net accumulation starting from 0.6 seconds to x seconds? Yes, sir. All right. Someone else started to talk. Same thing? Yeah. Okay. So and I saw some of you had it. So this is what that net accumulation function is. It's m dx. Given any change, multiplied by the constant rate gives you the change in this case, height. Right? But now, that change is variable based on whatever that final time is. Right? That final time is increasing. So whatever that final time is, minus the 0.6 gives us the change in time. We've got our change in time. Multiplied by the constant rate gives us the net change in height. Anybody have a question? So that brings us to principle 2. Principle 2 that's really important about our endeavor up here, number 2, is net accumulation function. Net accumulation function, which you just found an example of. You found a net accumulation function. So same situation. Soldiers lowering the American flag. How much does the height change from 0.6 to x seconds since the flag left the top of the pole? So I want you to sketch a couple of graphs here. First graph I want you to sketch is the rate of change function. And then I want you to sketch the net accumulation function. But here's what I don't want you to do. I don't want you to try to graph the equation you just wrote. Forget about that equation. Just erase that equation from your mind and don't use it. I want you to think about the situation and what would this mean? So before we do that, though, we need to get our units on our axes. So what about over here on the left-hand graph? What will our x-axis unit be? What are units? Seconds, right? Seconds gone by. All right, this is going to be our x-axis, seconds gone by. What will the units on the y-axis be over there? So some of you are saying meters per second. Okay, so I want x first. So actually, and then the accumulation function, it's the same x, number of seconds, okay? So both the rate of change function and the net accumulation function, we're talking about functions of x, the number of seconds since the flag started to be lowered. What's the units on our rate of change function? Meters per second. This is the rate of change of height, meters per second. What will the units on our net accumulation function be? Meters. This is the net change in height. Net change in height in meters. Okay, so I want you to sketch these, but again, I don't want you to be looking at the equation we just wrote and you know, thinking about algebra. How do I sketch this equation? Rather, I want you to think about the situation. I want you to think about the situation. Given this situation, what is the rate of change as x increases? And how would that graph emerge as x increases? And what would the net accumulation function look like? So you got to really discipline yourself to erase that equation from your mind and try to sketch what would the net accumulation function, meaning the change in height starting from 0.6 seconds, what would the change in height as x increased from 0.6 seconds look like?
Don't worry about plotting exact points. We're trying to see if you get the general idea about the situation. Okay?
Yeah, exactly. You're not building a table of values and plotting points and connecting the dots.
It's a sketch.
We're sketching. Sketch about how all the points would emerge continuously. Okay. People that I glanced at had the right rate of change function. Draw it with your finger. Constant rate of change. Rate of change. Rate of change.
I'm sorry, Mark, is that time is not since 0.6 seconds, right? That
Yeah,
time
so
is from when it first started blowing.
right. So this 0 is x, right? These are x, and so we're gonna we're starting from 0.6. Okay, so we're starting from 0.6 seconds equals x. So this doesn't represent 0.6 seconds. That represents x equals 0. And so here is 0.6 seconds. So this is where our net accumulation function begins. So here's the rate of change, negative 0.75. And you told me that at 0.6 seconds, what is the net accumulation of height since 0.6 seconds? 0. So then what's going to happen to the net accumulation as x increases from here? Our change is going to be greater and greater negative. So that's what that looks like, the net accumulation starting from 0.6. Anybody have a question? Okay, so we're gonna pick it up right from here on Monday, and you got your